Welcome, this is question 1 for AQA's Unit 2, actually starting Unit 2 past paper series, finally. As I said, this is the June 2015, this is question 1. Now, in this question, it's all about this glider that we've got given here. Now, we're told there's a force forward from a rope, really need to know that just a force pulling forwards of 7,200 newtons. There's a drag pulling it backwards of 1,200 newtons. The combined weight of the pilot and the plane, a glider, is 6,500 newtons. The vertical force of the lift of the glider is 7,500 newtons. Okay, and that's fine. The magnitude of the resultant force. Although we are told it's 6,100. Now, obviously, it's not going to be exactly 6,100, so don't be worried if you don't get it. I mean, generally, when you say show it is 6,100, when it's such a nice number like that, they will. It's not going to come out to be that. It'll round up to two significant figures to be that, because obviously that's what they've rounded it to quite clearly. Okay, so as I said, it's just about, really, I personally, what I would do is, I know just for me, it's having this glider thing. It's a bit, oh, what the hell, why they put a glider in there? They've just given a scenario, they've just related it to something. Really, what we need to do is we need to work out, well, what's the overall horizontal force, which way is it being pulled horizontally? So is it being pulled from where we're looking to the right, or is it being pulled to the left, forwards, backwards, or is it being lifted up or pushed down? Obviously, it would be lifted up, not quite clearly, but anyway, there's a concept of gliders, but it's a different thing. Okay, so it's obviously we take away 7,200 from 1,200, which obviously gets us 6,000 newtons. So we've got a horizontal force going forwards of 6,000 newtons, as we'd expect going forwards, obviously. A lift upwards, if you take these two away from each other, you end up with 1,000 newtons going up. So quite big values, but nothing to be too worried about. Okay. Now, as I said, I would just assume the single point is a glider. Now you could draw it on the glider, but you'd start getting a bit messy. So I'd draw it somewhere else on your page, obviously at part A. Okay. And then our resultant kind of looks something like this, where it's probably better to draw the dotted line box first. Now it doesn't matter if you don't draw this. This is just the way I think of it. Okay. We'll call this the resultant vector, okay? And then the resultant is just using Pythagoras from these two extremes, okay? So what you do is r is equal to the square root of 1,000 squared plus 6,000 squared, okay? And you sub that in your calculator. Sorry, no point putting square root again, because I'll just tell you what r is. And if you were to do that, you would get a value for r, which is ounces, 6,082.756 or whatever newtons. Okay. Now it said to find r the 6,100 newtons. So you just say, okay, well if you round that up, that's approximately 6,100 newtons. Obviously we know it's 6,082.75 whatever, but they've rounded it, as I said, to two significant figures. Now this next bit is asked us to find direction. Now think about it logically. It's obviously going to be pulled this way. It's obviously, if you look, there's a bigger force pulling it this way, horizontally rather than vertically. Okay. So personally, what I would do, the angle, obviously, therefore the angle, this angle here, from the horizontal to the resultant is going to be a lot smaller than from the resultant to the vertical. So I would calculate the one. It doesn't matter which one you calculate, because you will get the right answer either way. Okay. Hopefully, he says. Now it's just a case of obviously spotting these are right angle triangles and working it out as though you would work out a right angle triangle. Okay. So as I said, I'm going to kind of go through another step that you might not necessarily do because you want to save a bit of time. But this is a basic trick. So what we've got here is the hypotenuse and the adjacent. We want to find the angle between them. Okay. So the only one that consists of that is you thinking of SOHCAHTOA is cos. So it's r times cos of theta is equal to 6,000 newtons. Now you might have just put r to be straight away as your 6,082 0.75 newtons. Okay, now for some reason you couldn't work out the resultant in terms of you totally forgot how to do it. If you draw something like that and use the 6,100 they give you, you will get an answer which is slightly different, but they obviously will still accept it. But you will be deducted a mark for not having the proper resultant force. But if you get the direction of it, that is still considered to be acceptable. Okay, so don't give it on this question if you can't get resultant. But as I said, there's no reason why you wouldn't. Okay, so as I said, it's just a simple case of rearranging. I'm going to go straight to it. So it'd be theta would be equal to the cos inverse of 6,000 newtons over 6,082.75, etc. Now, as I said, I would just newtons. Now I would just continue. What you when you did this square root of 1,000 squared plus 6,000 squared, you get an answer for the resultant, and I would just keep that as your answer button. So save it in your calculator's memory, and to get complete accuracy, I would just shove it in to the theta value and find the cos inverse, and you would get theta. Okay. Now that theta, you would say, well, whatever you get value for that theta, you would put it to the horizontal for the resultant vector. Okay. And if you were to do that, you would get a value of 9.5 degrees. Okay. And you would say specifically that's to the horizontal, because the examiner doesn't know if you're considering this angle or if you're considering that one. And obviously if you're considering the one to the vertical, that's stupid, because that would not be about 9.5 degrees. Now, as I said, you only need to work out one angle. Obviously therefore the other angle would be 90, take that, it's logical, but as I said, you only need to work out one angle. Double check that's definitely right. I didn't check this, so probably should have done that. Yeah, as I said, it allows you from 9.4 to 10.6. Obviously, for the people that just use 6,100. So as long as you got it within that range, as I said, it's online. So, sorry, part 1AI was finding out the resultant, and 1A part 2 was finding out the direction. So I do apologise. I've kind of mixed part A into one question, which I do apologise. Okay, so now it's asking us to find the resultant acceleration of the glider in figure 1. Now it's obviously asking us to find the direction of that acceleration, because we've already found it in terms of the angle. Okay, but really all we use from all of this information we've just worked out, all we need is this resultant vector. So as I said, if you've put this in your calculator memory now, you might want to go back and do that sum again. So the square root of 1,000 plus 6,000 squared, and you would square root that to get whatever value it would give you. Okay, and therefore we would go on to say, so this is 1B now, sorry, not 1B, 1A part 3 goes on. Okay, so you write down what you know. So obviously you know R is specific 6,082.75. Now if you just wrote R is 1,000, R is 6,100, because you were copying the number in as you hadn't been able to work out R, that's still acceptable. Okay, but as I said, I would like to keep it as accurate as you can. Okay, so that's your resultant. And just for simplicity, I'm also going to call that equal to F, because really it's the resultant force. It's not just the resultant something, it's the resultant force. So as I said, that's what F is. You know the mass? Or do you? Well, obviously you know the weight of the glider, which is 6,500 newtons. Okay. So therefore what you do is you do your 6,500 newtons over 9.8, because we know the weight is equal to the mass times the acceleration due to gravity. Now for AS physics, you need to know that it's 9.81. As I said, it is 9.81, but you can make it a lot more accurate. And if you are in AS and want to figure out how you work out G, then please do check my A2 playlist out on gravitational, on the gravitational section between planets or whatever. Anyway, so going back to this. So you divide it by 9.81, just 9.81, you get a mass of whatever that gives you. I think it's 626, but I'm not sure. So 500 over 9.81, yeah, gives you 662.589, etc, etc. So you just leave, yeah, okay, so that's your mass. As I said, you might want to round them to whatever, doesn't really matter. You know F equals ma. You want A, so you just rearrange to get A. So A is equal to the resultant force of the mass, or if you just left it this as R, it's just the R over M. Okay, subbing what you know, so A is equal to the R, which is this 6082.75, etc., etc. Over your acceleration, which you just worked out, which is 662.58, etc. Okay, sub it in, you get a value for the acceleration, which you should get the acceleration as 9.18. Okay, don't forget the meters per second squared units on there, because it's not given them to you, so you need to provide them. Okay, so that's essentially 1A. Now we're going to move on to 1B, so I'm just going to give you a second to copy that down if you've not done it already, and because we're going to be moving on to part B now. As I said, it's still the same question, so don't worry too much. Although, do worry. Joking, it sounded quite bad, never mind. Alright, so moving on to 1B now. It's still the same question, I'm making it sound like it's a totally different question, but it's not. Okay, so what we're told now. We're told the glider climbed to a vertical distance of 600 metres, so first thing you write down is delta H is equal to 600 metres. I do apologise about my writing. Looks like 666, that's quite bad. 600 metres, it increases. Now you might want to draw that, it's up to you. Probably your page isn't long enough, but you get the idea. Okay, we're told it does that in 55 seconds, so you write T is equal to 55 seconds. Even though we might not end up using this all in the first little bit of 1B, it's always nice to have all of the information written down. Okay, the average power input to the motor during a launch is 320 kilowatts. Okay, so the first thing I would write is convert that to thousands. Okay, so the power, it's told us the average power is 320 kilowatts, which is equal to 320,000 watts. And we should know that power is equal to change in energy over the change in time. Units for energy, joules. Units for time, obviously seconds. So therefore we can also classify the units of power as joules per second. Okay. Now I'm not crazy. The reason I'm doing this for a reason. Okay. And also it's told you the average power, so it should be springing out at you even if you hadn't changed these units. Or you're a complete psychopath and just, you know, a rebellious little teenager and can't be bothered changing that. Whatever. Okay, so calculate the change in gravitational potential energy, the glider. So the first thing I would write down, weirdly enough, is the equation for GPA. Crazy enough, isn't that? Which you all should know is mg times delta H. Okay? So really, you don't need time, you don't need anything like that. All we need is the change in height, the mass, and the acceleration due to gravity. Now, as I said, you might want to put G is equal to 9.81 on here, but as I said, you should already know that. Okay, so the value for GPA, is M. Now, as I said, we just worked out M before. That was at 662.58, whatever it was. Now, you could just simply write in your list that that's what the mass is. But if you, as I said, it's up to you if you want to do the calculation again. It's a bit of a waste of time, really. But so we know the weight is 6,500 newtons. So proof before you just do 6,500 over 9.81, which gets you 662 newtons. Sorry, 662 kilograms. So that's the mass, so you just shove that in there. Obviously, the more exact figure of whatever it's. Okay, times 9.81 times the change in height, which is 600 meters. Or, as I said, because you've got mg there, as I've said, mg there, that's the weight. So you could just simply, instead of writing 662 times 9.81, because that's the division you did to get to go from 6,500. So really, you could just change them 2 points there. And that'll be same as saying 6,500 times 600 meters. Okay, so it's totally up to you. Probably the latter is a little bit quicker, but seeing as I said that second, you probably didn't think of that straight away. But you know, whatever. Okay, so you value for the GPA. Okay, so that should get you a value of so find it 3,900,000 joules. Now that's an awfully big number to me. I'm not such a big fan of that. So you can either put it in standard form or do what I did and do is 3,900 joules, a kilojoule, sorry, which is 3,900,000 joules, which is the same as 3,900,000 joules. So just to confuse you, really. As I said, the answer's online if I've confused you too much. Okay, now the next part is one of the percentage of efficiency questions. So it's quite a nice one. Calculate percentage of efficiency of the winch system used to launch the glider. Now this power, this 320,000 watts, or this 320,000 joules per second, is the power being put in to lift the glider. And we know it's gained, it's told us that the kinetic energy is, you just forget it. So it's negligible, we ignore it. So there's no point trying to calculate G, because we know obviously that's the total energy being power energy. Power is energy per second that's being put into this system. It's obviously going to be converted into GPE and kinetic energy, and then heat, friction, whatever. Okay, so surely we should include kinetic energy. Now, ideally, personally, for me, I would have preferred it if they did, but you know, for the benefit of the other people, it's nice that they have it. Okay. I know I'm probably seeming a bit crazy, like, for God's sake, just give us the kinetic energy. And it's like, sit your arms in the exam, I'm not doing this question. They've not given us a kinetic energy, I'm out of here, I'm having enough of this. Unfortunately, you can't do that. But anyway, nice try. Okay, so this is the energy that's been put into it, yeah? Per second. Now that's per second, but this is 55 seconds, and we've not included this yet, so obviously we have to use this 55 seconds at some point. Now, we know that's 320,000 joules per second, and we've got 55 seconds, so the total energy being put into the system is the amount of energy per second times the seconds that are in, that we're covering, okay? So that's the total energy that we can work out. As I said, you derive that from the change in energy, the power is equal to the change in energy over the change in time. But I've just used the units to explain that fact, okay? So we know the power is 320,000 joules per second. Okay? And we times that by the time to get the change in energy, which is, say, 320,000 joules per second times 55 seconds, which mine looks like 2 S's, which isn't good if you are familiar with your history. Or any human being in existence for that matter. Okay, so 320,000 joules per second times 55 seconds, that should get you 17,600,000 joules. So 17,600,000 joules, okay? Or in the way I did it before, it's 17,600 kilojoules. So it doesn't matter which way around you do it, as long as you either both keep them in joules or both keep them in kilojoules, okay? So this is the energy we've got out of the system, this 3,900 kilojoules, or this 3,900,000 joules. Okay, so that's the energy that we've actually gained from the system, in terms of that's the energy needed to raise it. But the actual energy, the total energy we've put into the system, okay, is 17,600,000 joules. So we've put an awful lot more in. So where's all this other energy gone? Well, obviously it's gone to the kinetic energy, but we're not including that. We're assuming it's just it doesn't move anymore. It's just stopped in midair. Okay, and we're also obviously that goes to the frictional forces, etc. Standard kind of rubbish in physics. Okay, so as I said, it's an efficiency question. So it's just what percentage has actually been utilised. Okay, so it's this. As I said, it doesn't matter which way you do it. I'm just going to do the 3,900,000 joules over the 17,600,000 joules. Or you could have just wrote 3,900 over 17,600. You get the same answer. Okay, you times it by 100, and that's your percentage efficiency, which if you work it out is 22%. So assuming this system gives no kinetic energy, no movement, it's 22% efficient. Now obviously that's pathetically poor, but we've not included the kinetic energy in there as well. So nothing's going to be 100% efficient. It'd be very hard to achieve that. But as I said, 22 is quite poor. But don't be put off by the fact it is so low. As I said, that's so low because we've not included the kinetic energy, and just sack that. We're not doing kinetic energy. I mean, it's not like it'd be hard. The examiners, I'm not complaining. So I'm the interesting complaint. You didn't give us enough work. Friggin' hell. That annoying kid in class, like, you forgot to give us some homework. Unfortunately, if you were in my class, that'd be me. But it seems most of my classes at A2 level are a class of 4. I've got a good chance of surviving the next 5 minutes running out of classroom as fast as I can. Anyway, back to the physics, okay? So this question really was just using your knowledge of GPA, ignoring kinetic energy. As I said, that last question there, I think they're all worth a 2 marker each. Oh, that was worth 3 markers. Okay, really, as I said, you know, for this, for the 1B, the first part that I did, when I saw gravitational potential energy, now this is completely wrong, so you can turn it off if you don't get confused. But I saw that gravitational potential energy and thought, energy. I know power is energy over time, and that power. And I just went straight into weirdo mode and did power is equal energy over time, and I got these 17,600 joules as, 17,600,000 joules, and I thought that was the gravitational potential energy. Then, obviously, when it asked me to work out the percentage efficiency of the system, I obviously got it to be 100%, which definitely isn't right. So as I said, that's just something to watch out for, but hopefully you're not stupid like I am, so you didn't make that mistake, so you can just have a little giggle to yourself and point and laugh at the screen. Yeah, I'm very touched. So anyway, thanks for watching, and we'll see you in the next video.